Okay, so good morning and welcome to the Machine Learning Coffee Seminar. So today we have uh, Arno Solin from the Department of Computer Science from Aalto University, and he will be speaking about stationary activations for uncertainty calibration in deep learning. And then so Arno is accepting the questions even during the presentation. So if you have any, please raise your hand or write in chat box and I will give you the floor to you. And the session is also recorded, so please accept that and then we can then go on. But please, Arno, go ahead.
Thank you. It's a pleasure to be here. I was just trying to remember when the last time was when I visited the coffee seminar as speaker, and that must have been maybe 1.5 years ago. And well, a lot of research has happened in the meanwhile, and this time I'm talking about some recent work that I've been working on with some of my students, which relates to deep learning. I'm perhaps sort of I entered deep learning maybe like later on my career. I have a background in more like probabilistic methods for like temporal stuff and so on. But then there are some nice links, and then the things that I've been more recently working on in deep learning, and then some of the things that I've been working on before, nicely sort of is combined in this work, or at least so I think. So as said, if you have questions, then feel free to raise your hand or raise your voice, and I'm happy to take those during the talk. So let's see if that's working. So as I said, this is joint work with two of my students. So Lassi is a first-year PhD student here at Aalto University, and Christabella did her master thesis with me. And this was something that then we joined forces with during the last spring, and it was then accepted to the NeurIPS conference, where it will be presented in a couple of weeks. So this is kind of a sneak peek to that. And I assume that many of you will be attending the conference, so please come and talk to Lassi and Christabella then at the poster as well. But great. Well, what is the outline? So I'm starting with some motivation. Like, why do we actually do this? Why are we interested in this stuff? And then there is an actual sort of introduction to some background. There's some technical things that are kind of required. Some nice old research from the 90s to know about to get started. Some parts of those are related to random networks, like untrained networks, and what sort of priors, like activation functions in use on those models. And then there is also some stuff, like some signals processing stuff that is sort of good to know to actually sort of like understand what it's all about. And then the actual beef here is creating activation functions with mimic properties of like wild use kernels or covariance functions in Gaussian process models. That's sort of the actual like the technical part. And then I have a bunch of experiments trying to highlight some of the properties, some of like very nice properties of these models, and then I'm concluding with a short recap. This all like should take maybe roughly like 30-35 minutes or so. But then if there's a question, then I guess we use all the 45 minutes right away. So let's go to the motivation. The question here is, what happens outside training data? And now sort of, because this is a machine learning seminar, you all are aware of lots of like machine learning stuff. So let's think of a binary classification problem. Like we have two classes, we have some data points, some training data from those. They are here in like this red, orange, whatever color here, and then these blue dots. So this data set, might have seen it before. It's known as the banana data set. And for a very long time, I actually thought it was some like empirical measurements of some banana related things. But then at some point, I was told that it's actually a simulated data set. And the thing is that here, like there's the shape here resembles a banana. But nevertheless, it's a nice data set. So in a binary classification problem, what you usually want to do is that you want to come up with some decision boundaries that separate these classes. And well, without any machine learning methods, we can just like use our like normal learning and see that there's probably some decision boundary here and one here, and then probably one here. But then the question here is that what sort of decisions should we make then outside data? For example, up here in the corner, there's no measurements here. So which class should then which should be the class that we would then decide upon if we would get an input point that would actually be here? Which color does it represent? I don't know. I'm pretty sure you don't know. And because the data set is simulated, and if we disregard that there's actually some function that is simulated from, there's actually no right answer here. So it depends on kind of our prior assumptions about the problem and sort of what sort of we know about the thing. If this would be an actual data set, some measurements of I don't know, banana length versus banana thickness, or taste versus, I don't know, something else, color. So then we actually might have some prior knowledge and prior understanding what should happen outside these measured data points. But often we don't. So then it actually makes sense to have different options. So then if we think of here on the right side, we have a kind of representation what a neural network with a rectified linear unit, like a ReLU activation function, would kind of give you if you would apply that to a model like this. So the ReLU, if you might know, it has this sort of very sort of simple shape. So then it actually what sort of priority induces on this problem would be that it would be very certain about the class outside the training data points. So here the coloring outside the data points actually represent how certain we are about us. And here we would be very certain. The color is very light here about that it would be of this sort of bluish class. And the same goes here, it would be rather certain here that it's of the red class, and then these boundaries here separate the classes. Then again, if you take another paradigm in machine learning, like the Gaussian process model paradigm, where you put a Gaussian process prior on some latent functions, and then in this case you do a binary classification. You have a logit or probit likelihood. So then with a Matern, in this case, like a Matern covariance function of special smoothness degree, the covariance function would induce a prior that would be very uncertain about what happens far away from the training data. It would still have the predicted class the same, but here you see that the color is very dark outside. So then when you predict, it would be very uncertain. It would say that, well, I don't really know. And this is actually something that we quite often would like to encode in practical problems. You might have a classification problem that you train on, I don't know, images of cats and dogs. So the model only knows about cats and dogs. So then what should the model then decide if you show it a picture of a car, for example? It only knows about cats and dogs, and then it suddenly sees a data point which is very far away from all the cats and dog data points in the input space. But then it, for example, with a ReLU activation function, it would still be very certain about the decision. But then, well, there's the world is full of activation functions in neural networks. So then they all encode a different kind of they induce a prior on the problem. So then in this work, what we try to do is to try to get the neural network part behave a bit more like the problem or a paradigm here on the right side. So to be uncertain outside the data points. Okay, that's for the motivation. Then the longer story starts. So this is all related to deep learning with probabilistic principles, where sort of you try to like not only capture like point estimates and very sort of like direct approaches for estimating sort of one outcome, but you actually want to see like probability distributions or the predictions, perhaps over the like network weights, or then just look at the things from a probabilistic perspective. This also relates directly to like Bayesian deep learning. Like all these terms are a bit sort of interleaved, but what we here try to do is to try to encode priors in your network models a bit similarly as we would do in the Gaussian process like machine learning paradigm. And as I said on the previous slide, especially if you're interested in what happens outside the training data. So to allow the model to know that it doesn't really know. And we want to do that with a Matern prior. Why a Matern prior? Well, the Matern prior is perhaps the most used covariance function in GP models, probably because it's quite simple. It's easy to understand, it's easy to implement, easy to use. It's like everything is very easy about it. But it also has probably nice properties of like being stationary, which can sometimes be a bad thing as well. Sometimes it means that it's like translation invariant. So when you move the model in the input space, it doesn't really sort of care about that. Another thing why it's a nice family, it includes several other simple models as special cases with a parameter that you can adjust, which actually encodes sort of like mean square differentiability of the model functions. It basically means that you get these sort of very sort of stiff and like very smooth, like infinitely many times differentiable functions, or then these very, very flexible, not differentiable functions when you just like vary one parameter. And that's the same thing that we also want to do here. And a word of warning, like in Bayesian deep learning or like deep learning with probabilistic principles, very much of the interest has actually been in inference, how to do efficient like probabilistic inference, approximate inference with various techniques, be that then variational inference or sampling based methods or some nice tricks. In this work, we are not that much concerned with inference, rather with the sort of priors and models. And actually basically here in all the experiments, we just do the kind of the simplest, most straightforward thing. We use Monte Carlo dropout, which means that we basically apply dropout at prediction phase to get Monte Carlo samples of the output predictions. Good. So still to recap a bit more about sort of what I'm trying to introduce. So neural network has been an immense success story in actually solving many real world problems. You can apply them to huge data sets. They have been able to learn very, very flexible things, especially in things it's been challenging before, like audio and images and like understanding sort of these like complicated things that we humans understand well, but has before been problematic for many sort of machine learning models. But neural networks have actually sort of been very good at this. But then sort of they aren't quite there yet. So like they give impressive results, but the estimates are often like pointillistic, hard to interpret what they actually learned, and very hard to sort of trust that they actually learned that what we believe they did. So it's more like being based on sort of empirical like results, and then kind of like trust me, it works. So I would be a bit like cautious in applying some of the state-of-the-art neural network models to some safety critical applications. Well, then again, Gaussian processes are very sort of transparent in what they do. You can encode like prior knowledge, you get uncertainty estimates that are well calibrated, but well, this beauty comes with some costs that actually sort of applying these to the kind of problems like vision problems or audio problems or huge data sets in general is challenging. You often need to then to kind of approximate stuff a lot, which might then introduce problems as well. So then, like, neither here is perfect in any way yet. So then what we try to do is to sort of take some of the nice properties from the GP kind of models and introduce those to neural network models to bring things a bit towards a state that we would actually kind of be able to trust and rely on estimates in challenging problems.
Sorry, Arno, there's a question from Alex. So what does it mean to calibrate an uncertainty estimate?
That's a good question. So uncertainty calibration is actually a bit overloaded as a term. So with uncertainty calibration, I mean that actually sort of the uncertainty estimates that you get have a sort of a realistic meaning. They actually mean that if you say that the uncertainty here is high and here it's low, then it actually means that. Well, then of course, if you think of with a more like frequentist setup, then you can actually draw that the samples or the counts that you get out would actually sort of represent the actual sort of like odds that something might happen when you predict or so. A very bad explanation, sorry, but then it actually like maybe a meaningful uncertainty estimate would be more of the thing I mean.
Okay,
good,
great, but there's still another question. Sorry.
Great.
Yeah. Okay, but so also from Jon, can you comment on neural processes?
I can. This like neural processes has been actually a very nice sort of kind of similar-ish extension sort of in the like in the between of Gaussian processes and neural network models. They can actually capture many of the same things I'm talking about, but here I'm actually trying to like derive the connection under like random neural network connection, which comes next, for the activation functions that induce like matern-like priors in neural networks. But yes, they are very like much related to the same like problem setting, and there's a lot of work also like outside these two.
Okay, great, thanks.
Good. Okay, so then kernel of random neural networks. So this is actually going back to the 90s. So Radford Neal, who is kind of a well-known figure in this space, showed in the 90s that random, like sort of like untrained single layer feed-forward neural networks converge the GP in the limit of an infinite width. So if you have that's kind of is if you have a very shallow network, not a deep one at all, but very shallow and infinitely wide, so then you can see that as a Gaussian process. And this is kind of the link that is often discussed between these two. So what actually mean? So consider here that you have some nonlinear activation function and some weights and biases of a network. So then there is like a theorem that links these two, that the associated kernel that the infinite width neural network induces can actually be sort of written out as an integral of this form. And what is the practical meaning of this? It's maybe more of like a peculiar, interesting detail of that. If you have an infinite width network, they're actually a nice match. And then actually for several like activation functions, you can actually solve this sort of integral in closed form, and you actually get a kernel or covariance function that would be that of the infinite width neural network of that like single layer feed forward network. And of course, like in practice, like that closed form solution not always available, or it might be hard to obtain. So you can also then like take a Monte Carlo approximation of that integral and just like draw samples of the biases and weights and evaluate this integral to get sort of some understanding about the covariance structure of the induced GP prior for the neural network. So what does that actually mean then in practice? So if you consider such a neural network, the step activation, so then you end up with something called the Arcos 0 kernel, which actually here on the bottom, you have a very small neural network with just 50 hidden units. And you see that it's a bit sort of noisy, stochastic. But if you take that number of hidden units to infinity, you would get something that is shown here on the top. And for the ReLU, you get something like this. So with 50 units on the bottom and an infinite number of units on top. With the sigmoidal or like error function activation, with 50 units on the bottom again, and the infinite width thing on the top. With an RBF, you would get something like this. But then the question here is that, well, what is the activation function for the Matern covariance function? And that is actually what we are trying to look at here. So what we do, so the link between like neural networks and GPs, that's been around from the 90s. So you have some activation function and you have to work out what the inference width of like neural network, that is GP is. But we try to do the thing the other way around. So we have a GP model that's widely used and people like. So we want to take the arrow in the other direction to ask, what is the activation function that induces this behavior? And we do that by writing out the things in terms of spectral density, and then using some nice signal processing derivations for this. Why is this hard? Why hasn't this been done in the 90s? That was like my question when I started looking at this, because I thought that this would actually be something that would have been published in the 90s, or then there was some papers like the STEP and these like Arcosine covariance functions. They were published in the early 2010s or like late 2000s. So then I thought that someone must have derived this before, because like Matern covariance functions is the most widely used class of covariance functions in GP models. So then someone must have worked this out. And like we started looking at this, and turns out that for the RBF, which is a special case of the Matern, this has been also done actually already in the late 1980s. But turns out that many of those derivations rely on the fact that for the RBF under a Gaussian input density, this is kind of a technical detail, the eigenvalues and the eigenfunctions of the associated covariance operator can be derived in closed form. And then that makes the derivation actually quite easy. But this is not the case for the Matern covariance function, which actually makes sort of this route of like using Green's functions for derivations kind of very tricky. So I guess that's the reason that the same derivations that you could do with the RBF did not really work here. So then sort of people gave up. But here we instead take like a signal processing or like control theory route for this problem, which turns out to be actually very feasible. So I've been talking about the Matern a lot. So the Matern covariance function has it's a kernel that has a very kind of ugly but easy to understand parametric form, where there is a couple of hyperparameters. One is sort of like a magnitude scale, which I just ignored here. One is a characteristic length scale, which sort of tells about that how quickly like things vary in the input space. And then there is a smoothness parameter, which tells about the differentiability, that how edgy kind of the the sample functions are allowed to be. And the RBF, the squared exponential, is a special case when you have like infinite smoothness, like when this parameter nu here goes to infinity, then you have sample functions that you can differentiate infinitely many times. They are like extremely smooth as something gets. But then typically the Matern is used with sort of like half integer smoothness meter orders, which sort of tell us about the once differentiable, 0 times differentiable, 2 times differentiable or so, which tells us that they kind of are allowed to sort of change faster than just like being infinitely smooth. I'm just going quickly through derivation here because there's a lot of technicalities. So I don't think actually like using time is this talk for all these details makes sense, but they're all written out in the paper and some details in the paper appendix. So please have a look at those if you're interested. But basically what we do is that we leverage like spectral duality, like the Wiener-Khinchin theorem that says that if you take a Fourier transform of a stationary covariance function, you end up with a spectral density which tells the exactly same thing. It's the same prior, but in like spectral domain. And we realize that you can actually like do a spectral factorization step for this quite easily, which gives you a transfer function representation of the spectral density. So the G here is a transfer function, which comes from like signal processing theory, and you might be if you've studied electrical engineering or take some courses back in the day in signal processing or control theory, you probably like recall that these are the bees that you feed in stuff into a system, and then you look at the transfer function of like how it transfers the kind of the noise or the impulses that you feed into a system. So then the transfer function is that quantity from those courses that you might have taken back in the day. So we recover the transfer function, and we take the stable part of the system, which gives the transfer function here, G. And then there's like a remaining like spectral density for like that inducing sort of white noise part, which we collect, basically encapsulates all the sort of constants and the parameters of the model. So then sort of there's further steps. So then we take the inverse Laplace transform of this, and then do some tricks to extend the activation function or the transfer function to the real line, which ends up being something like this. And this is actually now the transfer or activation in the input space. And turns out that this is actually the quantity that we are interested in. And that makes sense because if you think of like these random networks, so you basically have a random network where you kind of shake the network with random weights and biases. So that's actually kind of the same thing as feeding in noise into a system. So that's actually sort of makes sense that the activation and transfer function is kind of the same thing in this context. And looking back at sort of like 1980s or 1990s neural network literature, where actually the activation function was still called transfer function in the neural network literature, which sort of all makes sense in this context as well. So the Matern is like a stationary covariance function. And here actually sort of we have local stationarity in the same sense as in sort of the previously known like RBF neural network covariance function. And this comes from some like Gauss decay envelopes in the model. And this stems to sort of the parameterization of the infinite with neural network with sort of the Gaussian biases and the weights in the neural network. So we have local stationarity, not global stationarity. And that will show here as well in the plots later on. So what do these activation functions then look like? So this is the same equation I showed you earlier. So it's actually quite looks quite complicated. But then when you look at the plots of like this quantity here with various degrees of the smoothness parameter. So you see that actually sort of the exponential, the smoothness parameter like being half, looks quite horrible. But then with more smoothness parameter values, you get these sort of nicer like rather smooth bumps that you use as activations. And then actually sort of you can also show that in the limit of infinite smoothness, we recover then like RBF neural networks, like RBF activations as well. So like that, the theory all makes sense. So earlier I showed you the Monte Carlo way of evaluating that that integral that links the infinite width neural networks to their like kernel or covariance function they use. So here actually like we can now plug that activation function into that and just sample samples of the biases and weights and evaluate to look whether all what we actually just derived matches up with the theory. And turns out it does. So here you can see like the dashed line here underneath is sort of the exact covariance function or kernel, and then the noisy things here are then then the Monte Carlo estimates of the covariance function or kernel. And these light lines here are then just the same lines under other assumptions about basically the bias noise terms here. Might be a bit much to digest, so please look at the paper for more sanity checks here. Then if you have a background in neural networks, you know that you can actually use almost any nonlinear function as activation. And that's why, because you can basically use almost any. So then there are these commonly used ones because they have empirically shown to be good, and they have some good properties that actually makes them nice in training. The training actually converges to something. You don't end up being stuck in local optima, so on. So then there's kind of these checks that for good nonlinearities in activation functions. So do we pass these normal sanity checks? Well, these activation functions are not monotonic, so that can be a problem. But then not all widely used activation functions are monotonic in the first place. So yeah, but well, life is like that. It does saturate. It does to 0 for actually most x, which is actually kind of a bad thing. So it could be like difficult to optimize. And all of them are differentiable except that represents sort of the exponential covariance function, which is like these samples are not differentiable. So it's kind of understandable that the activation function is not differentiable. It's that this sort of this spiky peak here. And that not being differentiable actually means that it's quite horrible to optimize. So then that is kind of problematic. But then for smoothness parameters higher than a half, then you're actually you're good to go. So then I promised you some experiments showing some of the nice properties of this activation function. So first I have like a very simple 1D regression example. So I first show these for the same activation functions that I showed earlier. That's for the RBF. That's for the Matern. 3.2, and then the exponential. So here, if you're familiar with GP models, you kind of have an expectation of what sort of prediction should look like, and you can actually see that sort of the same more stiff behavior in the higher order smoothness things, and then this more like less stiff stuff happening with lower order smoothness, and then this sort of non-differentiability starting showing in the exponential covariance function case. And then here they do not quite match here, but then basically we have to remember that here things have been trained from scratch. So like the hyperparameters have been optimized for the top row, all the weights have been optimized for the bottom row, And then like the bottom row is also like locally stationary, while the top row is like globally stationary. But the same behavior is sort of present there. So I think this looks good. Then I showed you the banana classification thing. These were the results from before, and now we have a result for the matter as well. It's horribly noisy. That's basically because we only have like 50 hidden units, but it shows similar behavior as the RBF, and it captures sort of what we would like to see there. And of course, like doing something else than Monte Carlo dropout, applying some one of the more fancy inference schemes, or then, for example, doing sampling would solve like the ugly noisiness case here. I have some more examples. We did some examples and experiments on UCI classification benchmark tasks, where basically we compared to like these neural network plus GP hybrid models, where you have a neural network and then like previous work has plugged in a GP at the end of the network to use the neural network outputs as inputs for the model and then predict things. And this is actually quite a good thing to compare against, because now we can do the same kind of model. We can have the same prior on things, but without that GP part. We just use the Matern activation instead of that GP. So we kind of have the same model that we want to have, the same assumptions, but we can do that purely in the neural network kind of paradigm. And then I'm also including here just like a vanilla sparse GP model for comparison. So here are results with the Matern 3.2 prior. We also have results with other like Matern smoothness degrees in the paper and supplement. But we can see that we actually sort of do very well in terms of negative log predictive density. That kind of also like summarizes some of the uncertainty and like out of sample predictions, but we also do well in terms of accuracy and area under the curve. So this all is sort of like very encouraging, because even though we have the same model, we should kind of in the ideal case, we kind of should be matching. If everything would be like ideal, like the GPDNN and SVD-GKL models should actually be exactly the same as for the Matern activation functions. But there, they need to approximate the GP, do approximate inference, do sparse methods, or some like things for speeding up the GP inference, and all those approximations take a toll. So then actually like doing it all in the neural network paradigm with the Matern activation actually simplifies things, makes training a lot faster, and speeds up things, and also gives you better results. We also looked at Cypher10, which is this image data set with these like here there are 10 classes of images that should be classified, and we do this under like a out of sample experiment where we train on only 5 classes of different images, like planes, cars, birds, cats, and deer. But then at prediction time, we have all 10 classes present, and now the model doesn't really know about those other classes, and we have now like ship, truck, frog, dog, and horse included. And of course, now you look at the classes and see that we have actually picked them, that they are kind of similar, but still different from the ones that we included. And there's a lot of comparison in the paper, but I just include sort of this one plot here. So basically, if you use a ReLU activation, the trained model doesn't actually understand that there are kind of out of samples at testing phase. So it just mixes everything. You see that by looking at these histograms, that it actually doesn't see any difference between those classes that it hadn't seen at training phase and those that it had seen. It thinks they're all the same. But then with the Matern activations, it actually sees that the known classes and unknown classes have a clear separation. It's like from the start, it's more uncertain about the things that it hasn't seen. And also, if you actually then look at the results, basically tails of these histograms, you can tell that the ReLU is just mixes everything and doesn't really sort of kind of get that, well, there's no logic in sort of the predictions. But then actually, if you look at the matern cases, and even though it needs to be labeled things it hasn't seen, it actually sort of like puts together like car and truck, dog and cat. So it knows that they are similar, but it still gives them a higher uncertainty. That's a good thing. And the final experiment we had was related to like radar emitter classification, how to recognize what kind of aircraft you have from the radar signal that you observe. And that's also a very important thing, that if you actually try to do this sort of learning based, that you train with training data, and so then you want to be uncertain about that you actually don't know about. So in these kind of applications, it's very important that the model kind of knows that it doesn't know everything. Recap. So we introduced a new family of nonlinear neural network activation functions that try to mimic properties of the matern kernel in GP models. And these activation functions take with them some of the appealing properties and the nice things from GPs, which especially help out of sample uncertainty estimation in neural network models. There's code available, the paper in archive, and I have some references included about some of the background stuff and the previous work. And please ask questions now. We have a couple of minutes left, or then, well, if you don't have anything else to do, please follow me on Twitter. Thank you.
Great, thank you, Arno. So we have already lots of questions here. So maybe Sami, you would like to start.
Hi, Arno. Thanks for the great talk. So I can definitely see this highly interesting and useful. What I was missing, that you indeed did have the calibration in the title. So are the results calibrated, and are the results after the dropout sampling, are they equally well calibrated, maybe asymptotically as the original GP would be? Are you making claims of that type?
We actually discussed that. So we are making claims that in the infinite width, we actually get a perfect match. But then we don't do any claims about in the finite like sort of finite number of nodes. So our empirical results show that there clearly is better calibration than for like other neural network activation functions. But I would still be cautious with sort of putting this in a self-driving car to watch out for children, or a medical application where you need to decide like big decision about life and death. So then there's still like work required in that space.
Yeah,
very good
definitely point. Yeah, definitely you would rather put this than other neural network methods. But would you put this in same places where you put GPs is maybe the question. But I think you answered this. Thanks.
Yeah.
Okay, great, thanks. And then there's question, I am new to machine learning, but how can you do prediction to the data which don't have analogies in training set? All machine learning is about predicting data similar to training set.
That's also a very good thing. And maybe sort of I should have like put more emphasis on that side. So if you go back to the very start, the motivation. So remember the banana data that I showed. So now, of course, as you said, in machine learning, we make predictions about data that is like you should show the model data from the training set, and then that's what it sort of then learns. But in reality, you cannot observe everything. So when you then deploy a model, there will be data points from this part here, from this part, from this part, from this part, and you're still using your model for giving predicted labels for those. And that is the dangerous part. And this you should remember when you start deploying your machine learning models, that you're doing that anyway. Because if you would have observed everything, you wouldn't need machine learning. You just do table lookup and check that what you had before. So then here, the thing is that we want to encode assumptions, because anyway you're making assumptions, whether you know it or not. You're making assumptions in your model about what happens here outside. And now I just want to make it clear that, well, because you anyway do assumptions, then do an assumption that you actually know that you do. So if you use ReLU, then you assume that, well, I'm pretty certain that this blue stuff continues here. But if you use, in this case, a matern activation function, then you make an assumption that I don't really know what happens here outside the data. Good. I'm very glad that this came up, and I hope that
I'm sorry. So, sorry, can you hear me, Arno?
I can.
Yeah.
Sorry. So sorry to jump in, but I'm pretty sure that the question was asked by somebody else. But I think what they meant is, what about the orange, or no, the brown, or the pink, or the green dots? Like you I think that was a bit confusing when you started talking about the trucks and stuff. So I think that question was probably more about that than the uncovered areas in the space.
That's good. Okay, I'll continue with that then. So then here the problem is binary. So then we assume that we only get, for example, we only get cats and dogs as training labels. But then if you then deploy your model, you have this cat and dog detector at your door. So then one day, a hedgehog shows up at your door. And then your cat and dog detector, what should it do? So because it only knows about cat and dogs, so it probably classifies the hedgehog to, I don't know, a small dog, maybe, I don't know. But then what you probably would like to tell your model, that if you see something that you haven't seen before, that you don't really know about, then at least raise a red flag, or say that, I think this is a small dog, but I don't really know. I'm this much uncertain about that. So that's kind of like the other thing. So it's not only about what happens outside, but then basically also all those classes that you haven't trained on, that you didn't know about, or you didn't have time to cover, or you just ignored. So those classes all would show up here as Teemu said, pink dots or brown dots or whatever color dots here outside. So in that case, your cat and dog detector would probably be better off saying that I don't know about hedgehogs. Yeah. Did that help? Teemu, were you happy with this?
Yes, it helped me, and I hope it also helped the person who asked.
Yeah.
Great.
Okay, great, thanks. And now last very quick question, because we are running much over time, but then how expensive on time wise is training with matern activation versus ReLU or other classic functions?
That's also a very good question. So basically, because it's only a different activation function, and so like nothing else changes kind of in the neural network setting. You just have a different activation function. But then with that said, the training is slightly slower, because the kind of the peculiar shape of the activation function, of course, takes its toll. So, but then, for example, compared with having RBF as an activation, then it's pretty much like no difference. So then I think like Lassi would probably be the best person to answer this, because it was basically him and Christabella who then actually like went through all the troubles of implementing the things. But I remember that we looked at this, and like if I just throw out, let's say 10-20% slower.
Okay, so great. Thank you for the great presentation, Arno.
It's been a pleasure being here with you.
Yeah, and thank you everyone for participating and being active with the questions. So see you again next week. Thank you.
Thank you.
Okay.
Thanks.